For our first example, we are going to be looking at the first order series RC circuit. For our first order series RC circuit, we've got a circuit which is in series with a 50K resistor and a 20 microfarad capacitor. The voltage on this system is equal to Vs of t is equal to the square root of 5 times the cosine of 45 degrees plus 2t, and of course that's in volts. Be very careful, this is in degrees, this is in radians per second times seconds, and if you actually take those numbers and plug them into your calculator directly, you're not going to get an answer that has any meaning in it because you've mixed the variables in there. Like I said last time, I'm not quite sure why the textbooks do this. It's very sloppy form, but it is the way that it's typically done in circuits textbooks, so I have left it in the same way for you. When we look at this, we have to understand a few things about our system before we start even trying to solve it. So the important things to look at in our system when we want to get a holistic view of everything that's happening are really an understanding of the units that are within everything, the time scales that we're looking at, and of course the period of our AC signal. So if we want to talk about the period of this AC signal, we realize that we have the information sitting directly in our function. So the frequency is 2 rads per second times the number of seconds, or in other words, 2 radians. Now we know that 1 hertz is equal to 2 pi radians. So if we want to get the frequency out of this, and we know that theta is equal to 2 radians per second, then what we need to do is remove those radians and leave hertz directly. And recall that 1 hertz is equal to 1 over the period in seconds. So if we're going to do that, no problem. If we have 2 rads per second, and we take that and divide by 2 pi radians, we're going to be left with the number of seconds in our system, and that'll tell us what we actually need. So the frequency is equal to 2 radians per second divided by 2 pi, which is approximately equal to 2 over 6.28 hertz. And you'll realize that that's roughly equal to a little bit smaller than a third. And if you take a look at the signal, in actual fact, it's exactly what we would expect. It's 318.5 millihertz, which is roughly what we would expect when we take 2 and divide by 6.28. So that gives us an idea of how quickly this AC signal is moving, which will help us put into context the information about the transients in the system. Now we're ready to actually look at those transients. Recall that in an RC circuit, the transient is defined by some constant times e to the minus t over lambda. And for an RC circuit, lambda is equal to the resistance times the capacitance. So in this case, if we have 50K times 20 micro, then we have 1,000 times 10 to the negative 3, which is of course just 1 second. So in this case, our transient solution is going to look like C times e to the minus t over 1. Normally I would drop the 1, but in order to make sure that you realize I haven't forgotten about anything, I'm going to be trying to keep it in here within most of this lecture. And so this is very important. This gives us the information about the transients for the system. There's one more thing we're going to need to look at later, and since we're going to need to look at it anyways, we're going to take a quick look at it now. And that's an understanding of the initial conditions, because we're never going to get to the bottom of what any of this means if we don't know what the actual initial conditions are. So let's talk about initial conditions. You're typically going to assume that this source is off until time 0. So everything in the circuit is off, which means that initially the voltage in the capacitor is equal to 0. And I'm just going to make sure that that's clear, that the voltage in the capacitor from the left is equal to 0. But in a capacitor, we have particular equations that define how the capacitor works. And what we know is that I is equal to C dVc by dt. And because I is equal to the derivative, and if that derivative were allowed to change instantaneously, that would mean that that current would have to go off to infinity. We realize that can never happen, and practically that can't happen because in order to build a charge on the capacitor, you have to do exactly that. You have to build it. The current is running through, the electrons are going from one plate to the other, and they settle down in order to build a charge that matches what's needed by the rest of the circuit. So, if you're building a charge on this capacitor, not only is the voltage during time 0, 0, but the voltage on the right, immediately after you turn on the source, still has to be 0 because it can only change slowly. That doesn't mean slowly in time, it just means that it can't change instantaneously. Well, if we know that the initial condition on the capacitor is equal to 0, we can do a couple other things on this circuit. We can also look at the initial condition on the source. As soon as we turn it on, that's going to equal to root 5 times the cosine of 45 degrees. Of course, the cosine of 45 degrees is a triangle we're familiar with. This is going to equal root 5 times 1 over root 2, which is just equal to the square root of 2.5. So that's our initial condition on our source. And, of course, if we're going to go through the rest of this, we realize that Kirchhoff's voltage law has to hold. So the voltage in the resistor simply has to match whatever's left in the circuit. So in our circuit, we have Vs is equal to VR plus Vc, which means that VR is equal to Vs minus Vc. So we're going to take the initial conditions. Of course, the initial condition on the capacitor is 0, so therefore VR at 0 plus has to equal Vs at 0 plus has to equal the square root of 2.5. This is in volts, this was in volts. So now we know all of our initial voltages. We're also going to need to figure out our initial current. Our initial current can be figured out on the resistor, and typically we're going to be able to use a resistor to get whatever value was difficult or missing. It's difficult because if we were actually going to take anything else, we would need to solve the differential equation. But we're not trying to solve the differential equation. We're really just trying to solve a small piece of that. And so if we look at the last piece, the initial condition on the current, and notice I just write I because there is only one current in the entire system, we can find that by understanding the voltage on the resistor. V equals IR, so I is equal to V divided by R, which is simply equal to the square root of 2.5 divided by 50K, and when we take a look at that, this is going to equal 1 over 10 root 10 milliamps. So we now have the form of our transient solution. That's what we were looking for. And in addition to that, we have the important information that we're going to need later. So we know that we have our initial condition on our source, we have our initial condition on our resistor, we have our initial condition on our capacitor up above, and we have our initial condition on the current throughout the whole circuit. We highlight those because these are numbers that we're going to need to use later. And of course, that's all the critical information that there is in the circuit because the circuit has 3 elements, a source, a resistor, and a capacitor. And with those 3 elements, we know that we're always going to have the same current running through the entire circuit. Once we've done this, we've finished our transient analysis, it's time to move on and look at our steady state analysis. For the steady state analysis, the first thing that we're going to do is redraw our circuit in impedance format. So we have a voltage source, we have a resistor which has an impedance of 50K, and we have a capacitor. That capacitor has a capacitance of 20 microfarads. Looking at this, we're going to look at the different pieces of the circuit, and the first thing we're going to recognize is what our voltage source is. It has a magnitude of √5, an angle of 45 degrees. Remember, that's the phase shift in the original signal that goes into the circuit. And in addition to that, it operates at 2 radians per second. That last piece of information is critical because we actually don't know what we need to know unless we have that. So converting to impedance, this is our phasor for our input. We have 50K of real impedance over there, and for our 20 microfarad capacitor, we have 1/J times 2, that's the frequency, times 20 times 10 to the minus 6, that's the capacitance. So remember that J theta C on the bottom of a fraction is equal to a capacitor's impedance. If we take the numbers we have up here and rearrange them, we're going to see that we have the equivalent of 1/J times 40 times 10 to the negative 6. Move that up to the top, rearrange slightly, and we realize that we are going to end up with, before I say that, we're going to multiply by J/J. As we multiply that, we're going to end up with J times 25K. So remember that on the bottom, J squared becomes -1, so this value is actually negative. Our impedance here is minus J times 25K. So if we're going to draw this as an equivalent circuit, then we're going to place one impedance in it, and that one impedance is going to be 50K minus J 25K. With that impedance, we're able to start solving the circuit. We know the phasor for the source voltage. We have that up above. We know the equivalent impedance. We just calculated that. That's equal to 50K minus J 25. And of course, we're going to rewrite that. So 50 minus J 25, and of course the unit is K on both sides. So we'll just keep that as a unit on the outside. Now it's easier to look at this as 2 minus J1 times 25K, so that's what we're going to do. And the impedance in Cartesian format is useful and critical information, but it would be much more convenient for us if we actually had this impedance in polar coordinate form. So we're going to take it and convert it into polar coordinates. How do we do that? Well, the first thing we do is find the magnitude of this. The magnitude of the vector is simply equal to the square root of the real part squared plus the imaginary part squared. And we know that really we would be multiplying by the complex conjugate, and that's how we get this. We don't need to go through that formality. We can literally just pick out the coordinates and add them up. And then you take this and you multiply it by the unit on the outside. This is going to equal the square root of 5 times 25K. Now the next thing we need to do is look at the angle. If we consider the angle of the impedance, we know that we have the tan inverse of the imaginary part over the real part. The tan inverse of 1/2 is equal to, and one more piece, this was negative. So the tan inverse of -1/2 is equal to minus 26.5 degrees. So therefore, in polar form, ZEQ is equal to 25√5 with an angle of minus 26.5 degrees. We have our equivalent impedance in phasor form, both in polar coordinates and in Cartesian coordinates. So remember that a phasor is just a way of explaining the complex information. We're used to seeing it in the context of an Euler angle with a magnitude, but in fact a phasor is just a complex number. That complex number can be written in any format, even though for the majority of time we're typically most used to seeing that phasor in its polar form. Once we have this equation, we're ready to start solving the circuit. What are we going to do with this circuit? We're going to take a look at all of the equivalent voltages. How do we do that? Fairly straightforward. We now have the impedance, we now have the equivalent circuit, so the first thing we're going to do is solve for the current in the circuit. Once we have the current in the circuit, we can find the voltage in any element by multiplying the current by the impedance of that element. So let's start where we have. We know that the phasor for the voltage is equal to the current phasor times the equivalent impedance phasor. Well, that just means that IS is equal to VS divided by ZEQ. And the reason that we converted everything into polar form is because this is going to be much easier to work with. VS is equal to the square root of 5 at an angle of 45 degrees. We're going to take that and divide it by 25 times the square root of 5 at an angle of minus 26.5 degrees. If we take these pieces together, then as we do this, we have root 5 divided by 25 root 5, and these two are going to cancel. And this is at an angle of 45, and remember that the minus 26.5 was on the bottom. If we move it to the top, then we're going to be subtracting it. 45 minus negative 26.5 degrees. Take those two pieces together, sum them up, and we're left with the current phasor is equal to 1 over 25 times an angle of 71.5 degrees. Now that we have our current, all that's left to do is calculate the individual voltages in the other parts of the circuit. So in the other parts of the circuit, the first thing we're going to do is we're going to look at the phasor for the voltage in the resistor. The voltage in the resistor is equal to the current running through it. That's 1 over 25 at an angle of 71.5 degrees, and that is multiplied by the impedance. So V equals IZ. When you multiply by the impedance, you're multiplying in this case simply by 50K. Oh, and one thing that I missed before, I apologize, but this is my second time doing this lecture since I recorded it without sound the first time. So one thing that I missed is that this is in units of milliamps, and that is actually a very important thing to take note of. So as we move on to that voltage, if we take that current, milliamps, multiply it by the K, then we're going to get straight volts, and we see that we have 50 over 25 is the magnitude, and the angle is simply equal to 71.5 plus 0, because the 50 is purely real. Therefore, our phasor for our resistance is equal to 2 with an angle of 71.5 degrees. Last thing we need to do is do exactly the same calculation for our capacitor. Looking at the voltage in the capacitor, it's equal to the same current, 1 over 25, at an angle of 71.5. But now, instead of multiplying by a purely real number, we're multiplying by a purely imaginary number. The magnitude of minus 25K times J is just the same 25K. But in this case, the angle is different. Minus J points downwards, so this is negative 90 degrees. So if we want to take a look at this voltage and figure out what we've got, then we realize we have 25 over 25 with an angle of 71.5 minus 90 degrees, and this is going to be in volts because the K balances with the milli from the amps. So therefore, VC is equal to 1, and 71.5 minus 90 is equal to minus 18.5. So we now have all the information that we need in terms of the different parts of our system. We have a phasor for each and every part. We know the voltage in the capacitor, we know the voltage in the resistor, we know the voltage in the source, and we know the current that runs through the entire system. We have each of their phasors, so we're ready to plug them into our actual final solution. And we also know the transients that run through the entire system. So all we actually have left to do is turn around and put the pieces of this system together. In order to calculate what we did here, there are two computations that we needed to do that are a little hard to do without a calculator. One of them is taking a square root, and the other is calculating the tan inverse. Although you won't have a calculator on your midterms, you will have copies of tables which allow you to look up these values. So I want to point out how you go about using this. So we had the square root of 5 in one of our computations. We didn't actually need it, and I'd be perfectly fine with your leaving something in the format of the square root of 5. But I do want to teach you how to use this. If you have a graph for square roots, then you can take a look at the value and realize that the square root of 5 is approximately equal to 2 1/4. When you're doing this, obviously you can only be as accurate as the graph you're looking at. So that graph that we're looking at over here is pretty much not all that accurate, so it's going to be hard to get more accurate. That number may be off, but it would be more than good enough to do some initial computation. The other thing that we looked at when we used the calculations on the previous page was the tan inverse of 1/2, or the tan inverse of -1/2 to be more specific. Well, if you have the tan inverse of -1/2, then take a line across the half. Take that and pull it down over there. That's roughly 1/4 of the way into the whole graph. So therefore, the tan inverse of 1/2 is approximately equal to 25 degrees. Notice that's not as accurate as I got because I was using a calculator when I did my examples, but if you needed to work out your numbers in a graph, this would be exactly how you do it. You would take a look at the line where you have the value you're looking for, see where it intersects the actual curve, intersects the curve there, drop that down to the other side, and that is your frequency, and this graph is in degrees. Now that we have all that information, we're ready to solve some circuits. What do we do in step 3? We put all of our information together. So what is the critical information we have? Well, first of all, we know the source voltage, and that's exact. We don't need to calculate it, we have it. The source voltage is √5 times the cosine of 45 degrees plus 2t. Of course, that's in volts, and there's no transient on it. Why is there no transient on it? Because this is the forcing function. This is where things come into the differential equation. This is what causes the circuit to operate. And so there's no transients on it because this is direct. The transients, on the other hand, will be on every other part of the circuit. So let's write down the phasors and see where they land us. First of all, we calculated the phasor for the current in the system. That was 1/25 times an angle of 71.5 degrees. That was in milliamps. What does that mean? That means that the steady state value of current is equal to 0.04 times the cosine of 71.5 degrees plus our frequency of 2 rads per second, and that's in milliamps. So we have a steady state value. In order to look at our entire current, I of t, we need to add not just the steady state value, but also the transient. Recall that all of our transients had a fixed form. We know that the time constant of our system was 1, and so with that, the form of the transient was just c times e to the minus t over 1. plug that in, put it together, and we have the constant for current times e to the minus t over tau, which is, or e to the minus t over lambda, which is 1, plus 0.04 times the cosine of 71.5 plus 2t in milliamps. We can do this for each and every one of our circuit elements. So now we've got the voltage and the current from our source. Now we're going to look at the voltage on our resistor and the voltage on our capacitor. Notice we don't need to do anything else because the current in the source is equal to the current in the capacitor is equal to the current in the resistor, so we don't need to do any extra computation there. The phasor for resistor voltage was just 2 at an angle of 71.5 degrees in volts. So therefore, the steady state value of the resistor is equal to 2 times the cosine of 71.5 degrees plus our frequency of 2 rads per second times t, and that is in volts. If we put that together, the actual voltage of our resistor is equal to some constant times the resistance, e to the minus t over 1, not constant times the resistance, rather some resistor constant, times e to the minus t over 1, plus our steady state value, 2 times the cosine of 71.5 degrees plus 2t in volts. If we look at the capacitor, our phasor is just 1 with an angle of minus 18.5 degrees, and that's in volts. So therefore, our capacitor steady state is equal to the cosine of minus 18.5 degrees. Notice that that is 90 degrees out of phase with the resistor, plus our frequency of 2t in volts. Take that, put together our final capacitor voltage, and that's going to simply equal to some constant times e to the minus t over 1 plus the cosine of minus 18.5 degrees plus 2t volts. So now we have almost everything we need. We have the form of our solution for current. We have the form for our solution for voltage across the resistor, voltage across the capacitor, and of course we have the original voltage of the source, which is an exact value. So, with all this in mind, there's only one thing left to do. We need to figure out what these 3 constants are. In order to go back to calculate our constants, what we need to do is we need to take a look at our equations, which we've already gotten in the previous page, and we need to solve for those constants by using our initial conditions. Recall that we had calculated our initial conditions to start with. When we did this, we realized that the voltage of, actually let's start with current because that's first. We realized that the initial condition on current was equal to 1 over 10 root 10 milliamps. We realized that the initial condition on resistor voltage was equal to the square root of 2.5 volts. And we remember that in a capacitor, voltage cannot instantaneously change. Therefore, the voltage in the capacitor was equal to 0. With that information, we have everything we need to actually solve for the different pieces that are critical within this problem. So let's take a look at this. I0 is 1, or let's just change colors. I0 is equal to 1 over 10 root 10. That's equal to, and we're evaluating this at time t equals 0. At time t equals 0, e to the minus 0 over 1 is just equal to e to the 0. E to the 0 is equal to 1. So I can simply write down that value on its own. Then I turn around, I write 0.04 times the cosine of 71.5 degrees, and of course t is 0, so I don't have to worry about any other part. If I take this and I rearrange it, then I'm going to realize very quickly that all I've got is a value of a constant Ci is equal to 0.019. And that allows us to take this constant, plug it back into this equation, and we have an actual and complete equation for our system. Now we're going to do the same thing for our next two equations. So, looking at the voltage on the resistor, we know that the voltage on the resistor starts at the square root of 2.5. That's equal to CR times 1, because T is equal to 0, plus twice the cosine of 71.5 degrees. Therefore, if we rearrange this information, we see that CR is equal to the square root of 2.5 minus 2 times the cosine of 71.5 degrees. This is just equal to 0.95. Take that value, plug it back into the constant, and we have an answer. Lastly, we look at the capacitor. 0 is equal to this constant times 1 plus the cosine, and now we have a different angle of 18.5 degrees. Different because the phase shift on that capacitor is different from the other values. If we take a look at this, therefore, that constant is equal to negative times the cosine of negative 18.5. Notice the cosine is an even function, so I could have just written that that's equal to the cosine of plus 18.5. And when I evaluate that number, lo and behold, I'm going to have minus 0.95. I put that back in, and I now have equations that give me everything I need to know in terms of solving this circuit. That's great, because once you've solved a circuit, often you need to get some specific information about that circuit in order to actually be able to answer some questions. What do we want to do in this circuit specifically? We want to be able to understand a little bit about what happens over time. It's really important to understand what happens over time, because as things evolve in our circuit, we're going to have information being processed by these currents and voltages, and we need to basically understand it. So let's take a look at each of the equations we have. And I'm going to note that we're doing this for the time t is equal to 3 seconds. At t equals 3 seconds, we're going to have e to the minus 3, which means that our transient is settled to within 5%. So it's up to you in the application that you're doing, but in this particular instance, I'm going to make the statement that I can neglect my transients because of this, and once I do that, I'm simply going to actually evaluate the different extra pieces that we have of the sinusoids. So, no problem. What am I going to do? Let's look at the first one. The source voltage is equal to the square root of 5 times the cosine of 45 degrees plus 2t. And that, of course, is in volts. No problem, not too difficult. Plug that into your calculator or computer. But wait, this is in degrees, and this is in radians. That's going to cause me a little bit of a problem, so I'm going to do a little bit of computation in order to make sure that I understand what I'm looking at. So let's take a look at this off to the side over here. We have 2t, which is equal to 2 times 3 radians. Now, we don't need radians because we're doing this in degrees. So how are we going to deal with the fact that we have actually degrees and not radians? We're going to recall that 360 degrees is equal to 2 pi radians. So if I want to convert 6 radians into degrees, 6 radians is equal to 6 rad divided by 2 pi rad times 360 degrees. This is equal to 6 over 6.28 degrees. And if you take a look at that, times 360, sorry. Let's rewrite that so we can read it. which is equal to 6 over 6.28 times 360. And if you approximate that, that's going to be approximately equal to 345 degrees. In fact, if you plug it into your calculator, it's 344 to be more exact. So, you can get that, by the way, by looking at the graphs on the previous pages and actually making use of the approximations that allow you to change. So I have 2 pi radians. The only thing is that 6 wasn't in 2 pi, so I actually needed to convert that. That was roughly somewhere approximately up here, and that would have been able to give me the fact that we had approximately 344 degrees. So we have 345 degrees or 344, depending on how accurate you want to be. Let's actually turn around and plug that in. So this is equal to root 5 times the cosine of 45 plus 345, which is equal to root 5 times the cosine of 390 degrees, which is approximately equal to, or which is actually exactly equal to root 5 times, I'm going to subtract 360 off of there. As I do that, I'm going to be left with 30 degrees. And hey, that happens to be a number I know because the cosine of 30 degrees comes from one of my nice triangles, so I'm actually going to have an exact number of root 3 over 2. So, when I go back to here, I'm going to have root 5 times root 3 over 2, which is equal to root 15 over 2, but of course that's not super helpful, so if I plug that into my calculator, I'm going to get 1.96 volts. So therefore, Vs at 3 is equal to 1.96 volts. That's the source voltage, that's the value that we had that was exact. Now we're going to turn around and take a look at some of the other pieces within this. So let's look at our equations. Let's backtrack for a minute and write down everything we have. So we have the voltage in our source. We have the current in our source. Let's try and write that so it doesn't look like a derivative. We have the voltage in our resistor, and we have the voltage in our capacitor. We are going to go back. So we've grabbed each of the equations for our current, our voltage across our resistor, and our voltage across our capacitor, and we're now ready to actually turn around and apply the information that we have. So again, we're going to need to figure out what each of the different values are, so let's plug in the pieces. We have 0.019, and we're probably going to neglect this, but we're going to multiply it out in the first place just to see what it is, times 0.05 plus, and by the way, e to the minus t is 0.049787, so it leaves you with 0.0500 as far as the significant digits go, which is why I dropped it off there, plus 0.04 times the cosine of, and we're going to take 2t. We're going to realize that 2t is 345 degrees, so 71.5 plus 345 degrees. And of course, if we're going to do that, that's equal to 345, 345 plus 71.5 is 416. Subtract off 360, and you're left with 56.5 degrees. So this is equal to the cosine of 56.5 degrees. And by the way, you could very easily turn around and go to your graphs and do all of this computation work in your graphs on the other page. It would be less accurate. In the test, I don't actually need you to give me that. I need you to get to the punchline. But just so you realize, if you needed approximation, if I say approximate the answer, then you can use the graphs. So, if you take these two pieces and multiply them out, the cosine of 56 is 0.55. Take that, multiply by 0.55, 0.04, and you're left with 0.22. Now we're going to see if the transient did or didn't make a difference. So we're going to look at the transient 0.019 times 0.05 is equal to 0.00095. So essentially, I can cross that off. And what I see is that my value of current at time t equals 3 is equal to 0.22 milliamps. Next, I do exactly the same thing with my voltage, and we're going to take a look at the different pieces again. So we're going to evaluate the voltage at t equals 3. So voltage at 3 is equal to 0.95 times 0.05 plus 2 times the cosine of, and we've got the same angle this time, so we don't have to do any computation. It's the same 56.5 degrees. So notice that was 416 minus 360. So if we take a look at that, 56.5, take the cosine, that's 0.55, multiply by 2, that's equal to 1.10 something, and then I know right away I can see that I can neglect the 5% because it's going to be much smaller, because 1.1 plus 0.95 times 0.05 is plus 0.0475. So this is equal to, if we want, we can sort of keep a little pointer of that. We can say this is equal to 1.15 volts. So VR of 3 is equal to 1.15 volts. And lastly, we're going to calculate the voltage over the capacitor at the same time. So the voltage of the capacitor at time t equals 3 is going to equal negative 0.95 times 0.05 plus the cosine of, and this time I have something that's a little bit different because 18.5 is 90 degrees out of phase with everything else. So I'm going to take my original number, 345, I'm going to subtract 18.5, that's going to get me 326. I'm going to take the cosine of 326.5 degrees, and notice that's multiplied by 1. So as we're adding up the pieces for the voltage in the capacitor, the cosine of 326.5 is approximately equal to 0.83. And we're going to be subtracting off 0.0475. If we take 0.8, that's not what I'm typing, let's clear our memory in the calculator, 0.83 minus 0.0475 is equal to 0.78 volts. Therefore, the voltage in the capacitor at time 3 is equal to 0.78 volts. In order to make sure that we have what we're expecting, we're going to turn around and we're going to do a Kirchhoff's voltage law at 3 seconds, because we know that Kirchhoff's voltage law has to hold at all times. So, the voltage in the source at 3, is that going to equal what we got for the voltage in the resistor at 3 plus the voltage in the capacitor at 3? Well, on the left we have 1.96. On the right we have 1.15 plus 0.78. And if we take those two numbers and we add them up, we get 1.15 plus 0.78 is equal to 0.93, which is pretty close because we've got some rounding errors. So this is actually correct because we rounded a couple of things early. So we're happy because we see that Kirchhoff's voltage law works everything is where we expect it to be, everything is pretty good, and we've been able to solve all the exact equations for the time values. We've been able to figure out the transients, the steady states, the coefficients, and even apply that to get some voltages as time moves on.